Dear students, in this video, we try to learn spectral density function. The spectral density function of a signal defines the distribution of energy or power per unit bandwidth as a function of frequency. So in unit 1, we seen how to find out the energy and power in time domain. Now, when we want to analyze, for example, the speech signal, for the speech signal, if we want to analyze the speech signal in frequency domain, and as in that case, we can find out its energy spectral density or a power spectral density in frequency domain. So if you observe this, energy or the power per unit bandwidth as a function of the frequency we want to find out. So here we try to calculate energy spectral density which is in the frequency domain, which is the function of the frequency. So already we seen the Rayleigh energy theorem. So according to Rayleigh energy theorem, E is equal to integration or minus infinity to infinity x of f square into df. The energy of the signal x of t is a result of energies distributed by all the spectral components of the signal x of t. Okay, so the Rayleigh energy theorem not just provide a useful method of evaluating the total energy, but it also tells us that x of f square can provide us the distribution of energy signal x of t in the frequency domain. Okay, so the Rayleigh energy theorem actually gives us the total energy in frequency domain, and x of f square provides us the distribution of energy of a signal x of t in the frequency domain. So to distribution of the energy we can find out with the help of x of f square. So from this we can define the energy spectral density. The squared amplitude spectrum x of square is called as energy spectral density, that is ESD. So for the ESD, the notation here is psi of f is equal to x of f square, real part of x of f square. So this is called as the energy spectral density, which is the distribution of energy signal in the frequency domain. Okay, so with respect to this ESD, now we will try to see the properties of energy spectral density. Property number 1, the property states that the energy spectral density of a energy signal x of t is a non-negative real value function of a frequency. So see here students, the energy spectral density, that is psi of f, is the real value function. So that's why it is greater than or equal to 0. So psi of f is nothing but what? X of f square, which is the real part. So that's why it is greater than or equal to 0. That is squared of amplitude spectrum, which cannot be negative for any value of f. Property number 2, this property states that ESD of a real value energy signal x of t is an even symmetric function of a frequency. So ESD is the even kind of function of the frequency, that is the symmetrical. Property number 3, this property states that total area under the curve of ESD of an energy signal x of t is equal to the energy signal. So total energy E is the area under psi of f. So total energy, because already we seen through the Rayleigh power energy theorem what we are saying, that energy is equal to integral minus infinity to infinity minus infinity to infinity x of f square df. So and already we defined that x of f bracket square is nothing but ESD, that is psi of f. So in property 3 what we are conveying here, that total energy E is nothing but area under psi of f, that is the indirectly integration from minus infinity to infinity psi of f df. So psi of f means what? X of f squares. Okay. Property number 4 is also very important property for analysis of the LTI system. When an energy signal x of t is passed through a linear time invariant system, that is LTI system, the energy spectral density ESD of the output signal is equal to the product of energy spectral density of input and squared amplitude response of the system. So see here students, psi of f is nothing but the ESD of output signal, which is equal to psi of I, which is the input spectral density multiplied by squared amplitude response of the system. So in time domain, what we are doing, this is the input response x of t, which is gets applied to the LTI system. H of t is the system response and y of t is the output response. So proof for this property is very easy. Already we know to find out the output response of LTI system, we are using convolution, that is x of t convolved with the h of t. So taking the Fourier transform of both sides, so what we are getting, x of f, and we know that if you are doing convolution in time domain, we are performing multiplication in frequency domain, that is our convolution property. So convert the x of t into frequency domain x of f, h of t into frequency domain h of f, and perform here the multiplication, taking the squared amplitude on both the sides. So we are squaring y of f, we are squaring x of f, and we are squaring h of f, and squaring of y of f is nothing but the energy spectral density of the output. Squaring of x of f is nothing but energy spectral density of the input. So hence we proved that the energy spectral density of the output is equal to energy spectral density of input multiplied by squared response of the system. Property number 5. For an energy signal x of t, the autocorrelation function and the energy spectral density forms the Fourier transform. So dear students, we try to prove this property in our next video. Just see what this property conveys us. If you autocorrelation function is actually in time domain, if we try to take the Fourier transform of autocorrelation function, we will get the energy spectral density in frequency domains, and if you take the inverse Fourier transform of the energy spectral density, you will get the autocorrelation. So this is very important property. Based on this energy spectral density, we seen some numerics which are very easy. See, first of all, try to understand what is the statement given here. Determine the energy spectral density. So we have to find out psi of f, that is the ESD, and we know ESD is equal to, the formula of ESD is x of f bracket square. Here x of t, that is the time domain signal, is given a sinc to omega t. As I told you, for the sinc, the Fourier transform of the sinc is equal to rectangular, that is a upon 2w rect f upon 2w. And what we have to find out, we have to find out ESD. So ESD means what? Squaring of your x of f. So simply square for this rectangular which is in frequency domain. So we will get a square 4w square rect of fw. So this is what we find out here, ESD, energy spectral density for the sinc which is in time domain. Second, here x of t, x of t is given again the sinc, but what the question asked here, evaluate the total energy of the signal. Okay, so for the total energy of the signal in frequency domain, we are finding out with the help of Rayleigh energy theorem. So Rayleigh energy theorem, E is equal to minus infinity to infinity x of f square df. Okay, so the energy or total energy in frequency domain, already we have x of f, that is the x of f square, that is a square 4w square rect of f upon 2w. So just take the integration of this with respect to df, and it's a w is given here 2w, which is the width of the rectangulars, hence the integral limit is minus w to w. So after solving this integration, we are getting the energy which is in frequency domain, total energy, that is a square upon 2w. So dear students, once again I'll repeat, for this entire numeric we'll try to find out first energy spectral density, that is psi of f. The formula is equal to x of f, real part of x of f square. So whatever x of t which is in time domain signal is given to you, first of all, first step is what? To convert that x of t into x of f, means take the Fourier transform of the time domain signal, squared it, take the real part which is nothing but the ESD. Second, what is asked here, evaluate the total energy of the signal. So to find out the total energy, take the integration of x of f square. X of f square is nothing but your ESD, and take the integration with respect to df. Okay, see the next numeric, consider the decaying exponential function, find the total energy inside the frequency band minus W to W. So total energy means, again what we have to find out, E. E is nothing but what? Again here see, E is nothing but x of f square df. X of f square is nothing but what? ESD, psi of f. Indirectly we have to find out psi of f integration with respect to df, which gives us the total energy. Okay, so simply here already we know the exponential Fourier transform is 1 upon a plus j omega. So by considering that, we taken here the first of all we try to find out here what the Fourier transform of x of t, x of f, that is. Okay, so this is the x of f. Take the real part of x of f. So we perform here the rationalization. After performing rationalization, we are in position to find out the real part of the x of f square. So this is the real part of x of f square. Take the square of this, correct? After taking the square of this, take the integration. Integration limit is minus w to w. And now this integration, to make it easy, we use the integration formula. See here, this formula we are using, and entire integration is solved in our notes in detail, so go through it. After solving this integration, we are getting E is equal to 1 upon 16a. Okay, the next numeric is numeric number 4. Determine the energy spectral density and hence the energy content of the signal. So here x of t is given. Again we have to find out the energy spectral density and hence the energy content of the signal. So first of all, see here, we try to find out the energy of the signal. Okay, so then ESD, that is the psi of f. Psi of f is nothing but x of f square. So sync pulse Fourier transform is the rectangular signal. So rectangular signal squared is nothing but the ESD of the given signal. Okay, so in next video we will try to understand what is mean by power spectral density along with its property. Thank you.